Okay, so we're going to continue on here. Wrap up chapter 2, and after that, obviously continue on lecturing. So last time we talked obviously a lot about electron configuration and how to write proper electron configuration, how to do orbital diagram, which is again our boxes uh, that represent the different orbitals where we put our electrons in. Remember again, as we have a subshell that has multiple orbitals, so like a 2p, that they do fill based on 100 rule there upwards first, and then come back and pair up the spins. Remember, as we did for a number of the sort of electron configurations, you can assign quantum numbers for each individual electron. And again, our N, our L, our M sub L, and our M S type of values. We got into kind of transition metals, which are a little different, especially in terms of their electron configuration. Remember that when we do get into the transition metals, we are going to get into the d orbitals, and that important part of sort of the 4s, for example, comes before the 3D. So again, as we talked about, electrons will go into the 4s first and then start filling the D. And that is, again, the correct sort of electron configuration. So, if we had something like iron that we looked at, I think, got argon, 4s, 2, 3d6. And that, again, is sort of the correct order, not 3d6, 4s2. Also important in terms of transition metals, different than sort of the representative elements, is when we form ions. And when we form ions in representative elements, it's usually always the last sort of electrons, for example, that either gain the electrons or lose the electrons in electron configuration. Remember that with transition metals, there's sort of a switch in energy, and what ends up happening once you start sort of populating the d orbitals, the 4s actually becomes, for example, higher in energy. So when transition metals lose electrons, for example, they will lose the s electrons first, and then, if necessarily, they will come down into the d's and do that. So we talk about valence electrons, which are the highest energy electrons that are first away from nucleus. They're the ones involved in bonding, and obviously the ones gained and lost. In the sense of transition metals, they also do equal the group number. And for example, the group number we're talking about here is kind of the 1 through 18 group number, just kind of numbering all the groups all the way across the straight. And when we get to iron, there it is in group 8. Basically, there are 8b in some periodic tables, and that's how many valence electrons it has. For our representative elements on the outside, 1, 2, we skip the middle. I kind of go 3, 4, 5, 6, 7, and 8. The group number for these guys, the representative guys outside the transition metal region, will have also the same as the group number in terms of the valence electrons. So sodium has +1, or 1 valence electron. Aluminum, which is over here, technically in group 3A, or just group 3, will have 3 valence electrons. So a little different in terms of how electron configuration happens with ions for transition metals. Remember, there's also a couple of exceptions, a number of exceptions actually, but the two you're responsible for, again, is chromium and copper. And again, they have 1 extra electron up in the D, 1 less electron in the S, and it's just more stable in that sense. Any questions on electron configuration or any of that stuff we talked about there? All right, then we will continue on here and talk officially about the periodic table. So there's the periodic table. So the periodic table obviously contains elements grouped together by similar sort of properties. First off, there are groups on the periodic table. Not too many people call it families anymore, but most of the time they're called groups. As we've been talking about in a sense of the sort of valence electrons, there really are a number of numberings that you sometimes will see on the periodic table. For example, the one on the wall has it's really 1 through 18 in terms of its numbering. So you'll sometimes see that. You'll also sometimes see like an A numbering and a B numbering, like you do up here on the slide. For the most part, in most of the chemistry classes that you take, we use the A numbering, which is sometimes referred to as the representative numbering. And for that, basically, this is group, that is group 1 here. Group 2, we skip the transition metals 3, 4, 5, 6, 7, and 8. Again, a group coming down this way. We also talked about last time, and again, a reminder that it is lithium that's actually the first member of group 1. Although on most periodic tables, hydrogen's hanging out there, it is not part of group 1. Years ago, they actually would put hydrogen on both sides, actually. We also have periods, and periods go left to right on the periodic table. And as we talked about with electron configuration, there are 7 periods, essentially like your principal quantum numbers, basically your energy levels when you look at them as well. We also know that the number that we see above the symbol is the atomic number, which is the number of protons that we talked about in chapter 1. On the bottom is the atomic mass. Again, is the other number here. That's the atomic mass. All right, so let's talk about a little bit more of this. The periodic table is really broken up into 3 sort of categories. There are metals, there are nonmetals, and there are what's sometimes referred to as metalloids or semi-metals. On pretty much most periodic tables, that's like boron right there. You'll usually see this sort of outline of like a little staircases, sometimes referred to, kind of coming down. And to the left of the staircase, those are metals. Metals are good conductors of heat and electricity. They can be hammered into thin sheets. They can be pulled into wires. They typically have a very shiny appearance. Metals are pretty much solids at room temperature. The one exception is our friend Mercury. Again, if you look on that periodic table there, Mercury is in blue writing there as opposed to everybody else. If you go upper right of the staircase, those are nonmetals. And although not pictured on this periodic table, the 2 kind of rows on the bottom, those are also metals on the bottom there. They usually are like down in this area. That is also why when we look at the staircase here, the staircase is metalloids or semi-metals. Some books will include boron as part of that or make it a non-metal. The reason we talked about lithium here being member of group 1 is because that is actually hydrogen, and hydrogen, as you can see, is a non-metal, right? So these are metals here in group 1, and hydrogen is a non-metal, so it is not part of, like I said, group 1. And like I said, years ago, they used to kind of put it on both sides. Hydrogen has special properties and stuff like that. Now, a non-metal is pretty much the opposite sort of characteristics. They're dull, they're brittle, they're bad conductors of heat and electricity. Also different is the state. For the most part, you got a little bit of everything happening with our non-metals. We have some that are gases, we have some that are liquids, we have some that are solids. A lot of those diatomic molecules we talked about there at the beginning, like hydrogen, nitrogen, oxygen, all those halogens we saw yesterday as well, chlorine, fluorine, bromine, iodine. These are all elements that come as diatomic molecules. They're also all nonmetals as well. So a lot of those kind of diatomic elements are nonmetals. And a lot of them are gases, and some of them are liquids. Some are kind of like a liquid with a gas sort of vapor. Metalloids are semi-metals, as they're known, is that staircase, and you can see sometimes boron's included and kind of coming down as a staircase to the bottom. What are sort of metal, semi-metals or metalloids? Well, you can kind of see that they are like to the right of metals and to the left of non-metals. So our semi-metals there on the staircase will have properties pretty much similar to both sides. So the same element will have some properties that are very much like what you see in metals, and that same element will have some properties that you see in nonmetals, which makes sense in terms of their location, sort of the bridge between metals and nonmetals, or these guys that have kind of properties that fall on both sides, like some semiconductors and stuff like that. So that's what our semi-metals or metalloids are. Now, some groups do have special names, and you do need to sort of know these names. So starting with group 1, which again starts here with lithium. Those are the alkali metals. Right next door were beryllium, magnesium, calcium, where we looked at a lot of those guys in the experiment yesterday. Those are our alkaline earth metals. Also, we looked at yesterday over here at group 7 is our halogens. And those are our fluorines, chlorines, bromine, iodine. And to the right of there are our group 8, which is our noble gases. So group 1 and group 2, alkali metals, alkaline earth metals. By the way, the word alkaline pretty much means basic. So these two groups are where a lot of bases come from, like sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, magnesium hydroxide. You actually made a couple of these yesterday, probably. A little magnesium hydroxide, calcium hydroxide. Perhaps your litmus paper turned blue because you actually made some bases when it reacted with water when you put it into those guys. Our noble gases are guys that obviously are chemically inert. They're unreactive, and they're really important for a lot of things, including we touched upon, I think, yesterday as well. That's essentially the idea of bonding is like everybody wants to be like kind of the noble gases. Our halogens are mostly gases, and again, some gas and liquid type or vapor type things. You don't really want to smell too much of those guys. But group 8, as I mentioned before, are noble gases. Most people don't call them rare gases anymore. They're pretty much unreactive, but they will react with themselves, but really not other things. They're pretty much stable as you can get. The two bottom rows here, which are also metals, they, again, technically, if you follow the atomic numbers, we got 57 and 72, so that 58 actually should go right in there. And if we come down here, 89 to 114, so that 90 actually should go there. So these two rows here should actually go right there. They don't do that, otherwise your periodic table is really wide. I only teach at one school ever that I've seen that had done it, and they put it on a wall, and it takes up the whole wall because they spread out everybody to the right there to put those two rows in. Speaking of between group 2 and group 3, these are our transition metals in here. And transition metals, some of the properties of them are, for the most part, they could create multiple variable type charges. So for example, iron could be +2 in certain situations, +3 in other situations. Copper could be +1 or +2. Those guys, in terms of metals and so forth, and things typically outside of the transition metal region, actually I should kind of go above this staircase there. We'll typically have more of a sort of fixed charge, most of the things in those regions, but definitely transition metals have variable type charges. The two rows on the bottom, which is the lanthanide and actinide series, because those are the two elements they should follow on the periodic table, are also sometimes referred to as intertransition metals, because technically they should go kind of in the where the transition metals are. So sometimes they're referred to as intertransition metals, those two rows on the bottom. Any questions on that there? All right, so obviously you do need to know periodic tables. You need to know which way groups go, which way periods go. You need to know the names of the specific group 1 to the alkali metals, alkaline earth metals, halogens, noble gases, where the transition metals are, what things are metals, non-metals, obviously, and semi-metals. Any questions on that there? All right, so we're going to finish up talking about some periodic trends, and I'm going to add a couple here things to this one. We're going to also talk a little bit about electronegativity, which will be kind of the only thing from chapter 3. that you will need to know for the first exam. Pretty much kind of what we talk about in this chapter context of it. We'll also talk about effective nuclear charge. And that's what is sometimes referred to as Z effective, is effective nuclear charge. So let's talk a little bit about some of these trends, and we'll start with effective nuclear charge, I think. So when we talk about effective nuclear charge, or Z effective, it is this idea, for example, if we just take our friend lithium and we do a little electron configuration, 1s2, 2s1, it has 3 total electrons. Lithium's atomic number is 3, which means when we think about sort of our nucleus for lithium, it has a positive 3 sort of charge in it because of the 3 protons that are there. Now, we can see lithium is group number 1, and it does have 1 valence electron, which is this guy. That is the highest energy electron. These guys, again, are our core electrons, which are closer to the nucleus. So we can see, for example, here that on the first energy level, we got a couple of electrons kind of hanging out. And really on the second energy level, we got 1 more electron floating around. I'll just draw it like this for our picture purposes here. Now, when we talk about attraction, which is opposite attraction, electrostatic attraction, things that are positive and negative are attracted to each other. So these electrons would be attracted, obviously, to the nucleus. And the attraction in a sort of electrostatic situation between something that's positive and something that's negative is based on sort of or the strength of it is based on sort of the charge of it. So the higher the charges that come together in sort of a positive negative attraction will create a stronger bond than something that's like a lower positive charge and a lower negative charge. So if you had something like +3 and -3, they're going to be held together a lot stronger than, say, something like +1 and -1 sort of coming together. So what we're talking about here when we kind of look at the different electrons, obviously these being our core electrons, when we talk about our 2 sort of core electrons, which are obviously moving around randomly in this space, but these 2 sort of core electrons are going to pretty much feel the full sort of brunt of that +3 charge. So they're going to feel their kind of front row center there. They're going to feel the full sort of +3 charge, which means they're going to be pretty strongly attracted to the nucleus because of that. They're really feeling that overall +3 charge. Now, when we talk about our valence electron out there that is flying around, this one, this valence electron actually experienced something that's referred to as shielding. So this electron basically experiences shielding. And what that means is, frankly, the electrons that are in the lower energy level, the core electrons, are kind of like in the way of its full exposure to the nucleus. So it's kind of like when you go to the movie theater. Years ago, you could pick your own seats, I think. You get there early, get a nice center seat, right? And the movie's about ready to start, right? Somebody comes in with a big giant cowboy hat right in front of you, right? Shields half the screen, right? You're not seeing the full screen in front of you. So what happens here is because these lower electrons are kind of between that outer electron and the nucleus, they kind of shield it from the actual full brunt of the +3 charge. So you could actually calculate sort of what that electron is feeling in sort of the outside there by taking the sort of positive charge or the number of protons, which is basically +3 here, and we could think about how many electrons are in front of it, sort of shielding it. And in this case, there are 2, so we could -2 sort of charge. And what that outside electron or that valence electron in this particular simple example is actually sort of feeling in terms of attraction to the nucleus is actually only like a +1 type charge. So instead of feeling that full strong +3 charge like the core electrons are feeling, it's only feeling like a +1 sort of attraction, which means it is definitely not going to be held as tightly, right? And that is why those valence electrons, for example, are the ones that are removed or shared or involved in bonding, right? Because it's being held there but it's not being held, like as strong as something closer to the nucleus, which feels that sort of full positive charge. Now, electrons in the same sort of energy level do not shield each other. It's just electrons at a higher energy level are shielded by the electrons at a lower energy level. But that's the idea of effective nuclear charge. Effectively, that electron, for example, here in lithium, only feeling a +1 charge instead of that full +3 charge attraction. Any questions on that there? Now, that is one trend, and another sort of trend that's also important, and this is really from chapter 3, is electronegativity. And electronegativity is the ability of an atom to bring electrons towards itself. And when we look at electronegativity on the periodic table, electronegativity increases as you go this way, and it decreases as you go down. And the most electronegative element is actually fluorine. It's the most electronegative element you could have. Which does sort of make sense if you think about the experiment we did yesterday, right? When we talk about fluorine, it is group 7, and that is the halogens. And what we saw with the halogens, right, was reactivity increased as you went up, right? And fluorine is the most electronegative and will want to attract electrons. The only thing to the right of like fluorine and stuff like that is noble gases, which means they're not interested at all. They have like 0 in terms of electronegativity because they're really happy and stable the way they are. So they're not looking to bring electrons. They're not looking to change. They're actually really happy the way they are. So everybody else is trying to become like noble gases. So that's why we stop sort of with electronegativity there at fluorine. And really, when we think about noble gases, they kind of have really kind of no electronegativity or have a value of 0 when we'll talk about it in the next chapter. So electronegativity, which is technically from chapter 3, is that ability really of an atom to bring electrons towards itself. Fluorine being the most electronegative, and again, increases to the upper right, decreases left and down. Some other important sort of trends, as we talked a little bit about last time or yesterday in lab, is ionization energy. Ionization energy is the energy that's required to remove an electron from an atom in the gas stage. By the way, electrons are removed one at a time, so they don't all just like pop off. They actually come off one at a time. So, for example, if you took something like magnesium, the first thing that would happen is magnesium would lose one electron, and we would show the electron on the right-hand side of the arrow like it's being given off. The next thing that would happen is that guy that lost one electron would then lose one more electron. And maybe it continues this pattern. Now, when we look at this, when the first electron comes off, that is what is sometimes referred to as the first ionization energy. So the first ionization energy is the energy required really to remove the first electron. The second electron that pops off is the second ionization energy, the energy to remove basically the second electron. And creatively enough, the third ionization energy is the energy to remove the third, fourth would be the fourth electron, fifth, and so forth. Now, the general trend when we look at ionization energy is as you go on the periodic table up and to the right, it increases for ionization energy, our first ionization energy, and it decreases as you go down. So let's talk a little bit about sort of the idea of first, second, and third ionization energy. Is it easier to remove the first electron or the second? Which one would be easier to do, you think? Should be easier to do which one? The first one should be easier. What happens when we lose an electron, right? Something becomes positively charged. So if I have a neutral guy and I lose an electron, I become a cation, right? Which is positively charged. And that's sort of what ionization is about, right? When you lose electrons and become positively charged, you're going to become a cation. Does the size between the neutral guy and the cation, does the cation become larger or smaller? It does become smaller. You lose electrons. So you lose some of that electron cloud, everybody shrinks, right? So it actually, the cation is smaller compared in terms of size compared to the neutral guy because it's losing some electrons. That also means that because you lost electrons, you also now have more positive charge, right? And you have more positive charge, which means those outer electrons are now going to be attracted to the nucleus even more, right? It's going to be kind of pulled in and become smaller. So as we go from first ionization energy to second to third, the amount of energy increases a lot, as we can see here in the example of magnesium. As we go from the first electron coming off, it's about 735 kilojoules, not too bad. Goes about twice as much energy, right? To remove the second electron becomes a little bit harder to do. Then you want to remove the third electron, you're about 6 times or so the amount of energy to try to do that. Good luck with that. And why does that happen? If we look at the electron configuration for magnesium, it's 1s2, 2s2, 2p6, a little 3s2 action happening there. Magnesium, which is group number 2, has how many valence electrons? It is 2, those right there, right? So as soon as you get rid of these 2 electrons, which gets harder, you're now into 4 electrons, right? And that is why we see this incredible jump in terms of energy. It doesn't necessarily usually happen because it's not energy efficient. And that is why something like magnesium has actually a fixed charge of +2. It will only lose those 2 valence electrons. There's not enough energy to pull that third electron off, especially after you lost those 2 electrons. And that's why it has a fixed charge. So when we think about things on the periodic table, there are certain things that have fixed charges. Things in group 1 have a +1 charge. Things in group 2 have a +2 charge. Things in group 3, like aluminum, basically has a +3 charge. 4, 5, 6, 7, and 8. This is sort of where our semi-metals are. We have -3 for our group 5, -2 for group 6, and -1 for group 7. But right now we're talking about positives here as well. So magnesium, which is group number 2, has a fixed positive charge because you get into those core electrons. It's not going to happen based on energy. Any questions on that there? And that's what we see if we do look at sort of this table as we just looked at magnesium. Valence electrons gets harder, big jump into core electrons. Same thing with aluminum. Aluminum's group 3. It has a +3 charge. To remove the first one, not too bad. Second one jumps. Third one jumps, but now you can see the giant jump there after you get rid of the third valence electron. It goes from like 2,700 to like 11,000. Not going to happen again. This is why something like aluminum will also have a fixed charge. Um, So the trend in ionization energy increases as you go to the right, decreases as you go to the left. Also, again, every electron that comes off, it gets progressively harder because everybody gets kind of brought in closer and closer, going to be held tighter and tighter as well. So in general, as we go across from left to right, as we talked about, we will see ionization increase. Electrons are added to the same principal quantum number, and they're not completely shielded. And we also have that increasing nuclear charge caused by the added number of protons. We got more protons and electrons as we start, again, sort of losing electrons as well. All right, so in general, as we go down a group from top to bottom, ionization energy does decrease. And because as we go down on the periodic table, the atomic number increases, right? As you go this way as well, from top to bottom. That means that there are more protons, right? And more protons means, again, a positive charge. But in a sense with that as well, there's also more electrons, right? So there's more electrons going to be further out in a higher energy level, going to be further away from the nucleus and not going to be held as tight. In addition, going to be experiencing a lot more sort of shielding going to be happening in that. The idea here is when we talk about that Z effective that we talked about earlier, Z effective increases as you go this way on the periodic table and decreases as you go this way. So again, because of the number of electrons and that kind of smaller sort of effective charge, we're going to see it easier to sort of remove those electrons. All right, so we won't worry about that too much. All right, so let's take a look here. Which electron would require more energy to remove an electron? Should it be sodium or chlorine? Which one makes more energy? Yeah, so like on the periodic table, they're kind of like that basically, right? So chlorine is further to the right, which means it should have a higher ionization energy. It also has a stronger effective nuclear charge, which means even those outer electrons are going to be held tighter as well, right? Because of that. So it's going to be that chlorine in this case. Which one would require more energy to remove, lithium or cesium? So they are in the same group here, right, on the periodic table. Cesium is further down, and again, ionization energy decreases, right, as you go left and down on the periodic table, which means lithium should require, right, more energy to do so. Also, same idea, since Z effective decreases as you go down, lithium is going to experience those outer electrons, right? A stronger positive charge than we will see with this guy as well. So it'll be easier to remove the cesium and harder to remove the lithium. Which one should have the larger second ionization energy? Lithium or beryllium? Well, second ionization energy is the energy to remove the second electron, right? So if we look at the electron configuration for lithium, it is, bless you, 1s2, 2s1. It has one valence electron, right? If we look for beryllium, which is 4, it has 1s2, 2s2, has two valence electrons, right? Equal to the group number. So if I'm going to remove the second electron in lithium, I will end up with what type of electron? Valence electron I'm removing or core electron? Yeah, I'm going to end up removing this guy, and then now I'm into the core. Should that be easier or harder to do than over here with beryllium? When I remove the second electron, it is a valence electron, right? So it should be lithium, because that would be like trying to remove a core electron. For beryllium, it's going to still be a valence electron. It's going to be harder than the first one, but it'll be much easier than trying to rip off a core electron that we would see there in lithium. Yeah. Any questions on that there? All right. Talk about another trend. So we talked about ionization energy, which sort of relates to cation formation. Electron affinity is the energy change that occurs when an atom gains an electron. And when an atom gains an electron, they will become negative charge, or they will become an anion in a sense. So when we talk about ionization energy, we kind of think about it in terms of cation formation. Electron affinity is what we think about when we think about anions being formed as they gain electrons. Electron affinity and electronegativity are different things. So electronegativity, again, is the ability to bring electrons towards itself. electron affinity is actually the energy change that occurs when they actually gain an electron. So they are different things. Sometimes people think of it as being the same sort of idea. This equation is written like this, like the electron is being added here to the element and will become negatively charged. The general trend in electron affinity is it increases as we go up and to the right and decreases as we go down and to the left. So as we go up and to the right, it does increase. It's not a perfect sort of trend. For example, if you look at the energy change for the halogens, what you will see is as you go up, say in group 7, as you go up, it will start to increase, but then it'll kind of come back down and decrease. So it's not like a perfect trend, but the general overall trend is sort of up and to the right in terms of the energy change that occurs when they gain electrons. You will see sort of it increasing more negatively in terms of the energy as it kind of goes up there and to the right. Now, all of these trends also basically affect things like atomic radius. By the way, we just talked about earlier what happens with a cation. Let's talk about the difference between a neutral guy and an anion, right? So is the anion going to be smaller or larger or the same size as a neutral atom? The anion should be, which is negatively charged, it should be larger, yeah? And that's because unlike cations that lose electrons, anions are actually going to gain electrons, right? So their electron cloud gets bigger, and the overall size of the anion compared to the neutral atom will be larger because it has more electrons that it gained. In general, though, when we talk about neutral sort of atoms, as we go across the periodic table, we will see that everybody gets smaller, or it decreases, I guess is the better way to put it, and it increases as we go kind of left and down. Again, as we go to the right, we do have an increase in the number of protons, but we also see an increase in the Z effective, which is going to have those outer electrons feeling more attracted to the nucleus and being brought in. So the overall size of it's going to be smaller. As you go left and down, as we talked about, the Z effective, it's going to decrease and also going to have a lot more protons and a lot more electrons. And those electrons aren't going to feel as big of a pull in, going to give it a much larger sort of overall radius than we do see to the upper right on the periodic table. And as we get more electrons, the orbital sizes, as we talked about, does increase with each energy level. So again, that's going to kind of bring everybody sort of out. So here's what we see here. So how do all these trends sort of correlate to what we know happens with, say, metals and nonmetals? We sort of overlay our trends here on a periodic table, or maybe I'll just do, I'll do it here, maybe. So if we look at a periodic table, big circle, what we see is as we go up and to the right, we see electronegativity increase and then decrease. We see as we go up and to the right, an increase in the effective nuclear charge and a decrease coming this way. As we go up and to the right, we see an increase in ionization energy and decreasing coming this way. As we go up and to the right, our electron affinity increases and decreases. And obviously, as we see in terms of size there, our radius, it decreases as you go up and to the right and increases as you go this way. So as we go basically up and to the right on the periodic table, we have all these properties that say we have a very strong effective nuclear charge. So even the outer electrons are going to feel a strong pull towards the nucleus. It's going to bring it in and make it smaller, which means that it's going to take a lot more energy to try to remove an electron, which is why it has high ionization energy. it's going to have high electron affinity because it likes to gain electrons because everything's so compact as well. And it also will have high electronegativity because of that as well. Higher effective nuclear charge is going to want to gain electrons. So as we go up and to the right on the periodic table, they pretty much have all the properties of I like my electrons, I want to hang on to my electrons, and I would like to take your electrons as well. And that is typically what we see with nonmetals, which are up and to the right. They typically are the ones that will gain electrons and become negatively charged. As we go to the opposite end there of the periodic table, to the left and down, we have basically all the opposite sort of trends. We have trends of, you know, I'm kind of a larger sort of size, which means my outer electrons aren't feeling as strong of attraction to the nucleus. They're not going to be held as tightly. They have less ionization energy. I don't really care that much about bringing electrons towards myself. So as we go to the left and down on the periodic table, they have all the properties of I have electrons. I'm not looking to hang on to my electrons. You can take my electrons, please, and they are typically things that will lose electrons. And that's why metals, which are to the left of the periodic table, have all those properties of typically wanting to lose electrons and become cations and positively charged. That is also why, obviously, as you can see, down to the left is like, I want to lose my electrons. I'm not going to hang on to my electrons, which is why down and to the left is where you would find the most reactive metal, because that guy's like off with the electrons, right? And if it's able to lose the electrons really easily, it's going to be very, very reactive. As you go to the upper right, like we saw with our halogen experiment, what you have is somebody that's like, I want to hang on to my electrons and take your electrons, which means as soon as it gets an opportunity to grab electrons, it's going to do so, and that's going to make it very, very reactive. So that's why we were talking about yesterday, opposite ends of the periodic tables where you'll find the most reactive metal and non-metal, because they have all the extreme of these properties of I'm ready to go and ready to react. That's also what you should have saw with your metals as you went to the right in the same period. She got less reactive, right, than as you went to the left as well. Any questions on periodic trends and how they relate to? All right, so which one should be the larger atom? Sodium, chlorine? It should be sodium. Yeah, further to the left there. Which one should be larger atom? Lithium or cesium? It should be. Yeah, it should be cesium. Again, it's going to have that smaller effective nuclear charge. It's also going to have a lot more electrons, so they're not going to be pulled in as tightly, right? It's going to give an overall larger size to the atom. Which one is larger, the hydrogen 1s orbital or the lithium 1s orbital? What do you think? 50-50 chance. Which one do you think? Hydrogen or lithium? Are they the same? The answer is the one that should be larger is hydrogen, yes? So 1s orbital, we're talking about like the electrons there closest to the nucleus. The hydrogen electron is only going to feel a +1 attraction, right? Much stronger attraction with lithium, right? With that +3, which is going to bring these electrons in closer. And because it's going to come in closer, it's going to be smaller overall, right? Than those hydrogen guys that are not pulled in as far. So it should be the hydrogen 1s orbital will be not pulled in as close as you have with the stronger positive charge in the nucleus. That then should hopefully help you answer the next one. Which one should have a lower energy, the hydrogen 1s or the lithium 1s? Lower energy means further or closer to the nucleus? Lower energy is closer to the nucleus, right? So which one should be drawn in closer? The lithium, right? For the +3 charge, right? Gonna pull it in closer. So it would be the lithium 1s orbital in this particular case. Yeah. Any questions on that there? All right, here. We want to arrange this in terms of increasing ionization energy, oxygen, fluorine, and sulfur, and that obviously is it. When we look at it on the periodic table, it looks like this. So ionization energy increases as we go up and to the right. So sulfur should be the least, oxygen and fluorine in terms of ionization energy. Atomic size decreases as we go up and to the right. So fluorine should be the smallest, and sulfur should be the largest, going opposite, increases going in this direction on the periodic table. So fluorine, oxygen, and sulfur. Any questions about there? All right, so we talked about a lot of this stuff here. Again, the number and type of valence electrons do determine the atom's chemistry. As we'll talk about in the next chapter, it's all about bonding as electrons, and the electrons that are involved in bonding are those valence electrons. We talked about groups that have the special names and where they're located. Again, our transition metals, alkaline earth metals, and our halogens. There you go. What we talked about. And those are the alkali metals. Perfect. Any questions on that there? That is chapter 2. That is the last of the material that will be on our exam, which is Monday, by the way. And it will cover chapter 1, chapter 2. And again, the only thing from chapter 3 that you do need to know is electronegativity. The definition of it is, and where it increases, decreases in relationship to periodic trends that we just talked about. We're going to talk a lot more about electronegativity in the next chapter, but for this exam, that's all you need to know, for electronegativity. All right, we're going to roll into 3, and we're going to talk about bonding. We're going to talk about all types of bonding in chapter 3. Before we get into bonding a little bit, I think we talked about it just a second ago, but just to reiterate, probably be a little helpful here. Again, our number of valence electrons equals the group number. And we're talking about, again, really the representative numbering here. So again, everybody in group 1 will have 1 valence electron, 2, 3, 4, 5, 6, 7, and 8 here. So, but more importantly as well, in terms of charges, as I mentioned a second ago, everybody there in group 1 will have a +1 charge, fixed charge. Everybody in group 2 will have a +2 charge. Group 3, as I mentioned, pretty much that is going to be aluminum that you're going to be dealing with, will be +3. When we get over here, as I mentioned a second ago, and we're talking about the nonmetals, which are above the staircase, group 5 is going to be -3 fixed charge, group 6 will be -2, and group 7 will be -1 in terms of the fixed charge. These are our transition metals here, and they typically, for the most part, will have a variable type charge, but there are 3 transition metals that have fixed charges, and that is zinc and cadmium. They both will make a +2 charge. If you hang a left there at cadmium, you'll hit silver. Silver will make a +1 charge. So those 3 transition metals will typically have fixed charges. Everybody else in transition metal region will have a variable charge. And by the way, as I mentioned up here, when we're talking about above the staircase, which are non-metals have the negative charge, that's because below the staircase in this region, there's still metals, which should be positively charged down here. And these guys will, although they're not technically transition metals, will behave very much like transition metals and have variable type charges. So things like lead, tin, antimony, those type of guys as well will have variable type charges. All right, so let's talk a little bit about bonding. And one way that we can represent bonding is by using Lewis dot symbols. So sometimes just generically called electron dot symbols. And it basically is the symbol for the element and 1 dot to represent each of the valence electrons. There's really kind of no major rule, although most people kind of go clockwise and fill it up. The major sort of rule is we don't go more than 2 per side. And since each symbol will have 4 sides, a very important number in bonding is 8. and it should have basically a maximum of 8 sort of electrons on there. So we are, when we talk about these guys, each of these dots represents, again, the valence electrons, which are those outermost highest energy electrons that are involved. So we can use these Lewis dot symbols for covalent bonding and ionic bonding that we'll talk about to represent what is happening. And as I mentioned before, basically just the symbol and a dot to represent each of them. Again, the main rule is don't go more than 2 per side when you're drawing it. So here is sort of some Lewis dot symbols for all of our elements. Again, you can see everybody here in group 1 has 1 valence electron. Everybody in group 2 has 2, 3, 4, 5, 6, 7, and 8. One exception is helium. Yeah, helium is group number 8, but helium has only 2 electrons. It's 1s2, right? So that's the electron configuration. So clearly, because it only has 2 electrons, that is as much as helium could have. So it should only have 2, and everybody else there in group 8 will have 8. This is also why when we talk about 8 in bonding, it's really important. It's the octet rule. It's also why we will see and talk about that hydrogen, when it's bonding, should never go over 2, because all hydrogen has to get to is helium to become stable and have a really stable sort of relationship with electrons. So hydrogen, when it makes a bond, should only have 2. Everybody else should pretty much have 8. Some could go over 8, as we'll talk about, but that again is the reason why hydrogen should only really have 2. So let's talk a little about the 2 different types of bonding that we're going to talk about. The first type is an ionic bond. And an ionic bond is always pretty much between a metal and a nonmetal. And what happens when these two get together, because of those periodic trends we just talked about, my metal here is going to go take my electron. It's going to have a transfer of the electrons over to the nonmetal. That is going to create a positively charged metal, which is known as a cation. Going to create a negatively charged nonmetal, which is an anion. And it is this opposite attraction here, this electrostatic attraction, that holds it together. In an ionic bond, there is absolutely no sharing of electrons. So what is holding an ionic bond together is the attraction between a positive cation and negative anion, no sharing of electrons between anybody. And that is different than what happens in covalent compounds or a covalent bond. In a covalent bond, what happens is it's typically between 2 nonmetals. And if you look at where nonmetals are on the periodic table, they're all pretty much right there together. And what happens, because they are all pretty much in the same location on the periodic table, that means all those periodic trends that we just talked about, they pretty much have very similar trends. They all have, I want my electrons, I want your electrons, I'm not going to give away my electrons. So what happens when we get those two guys to come together is the best that they could agree upon is we'll just share electrons. I'm not going to give it away. I'm not going to take yours. You're not going to take mine. The best that we'll do is share the electrons here. And as we will talk about, it could be equal sharing or unequal sharing, but there is some aspect of sharing that's happening when 2 nonmetals come together, because they pretty much have the same ideas. They both want to hang on to electrons. They both want electrons. They're going to share. That's very different than what we have over here with an ionic compound or an ionic bond. We have a metal that's like, take my electrons. We have a nonmetal that says, thank you very much, I'll take them because I want them. And that's why we see the actual transfer of electrons from a metal to a nonmetal, because of that, the very difference in those periodic trends, because they're kind of like on different sides of the periodic table. But when everybody's together here on the same side, they both want to hang on to them. So the general rule is, as we talked about, things with low ionization energy will form positively charged cations. Things with high negative electron affinity, affinity basically means you like things, right, will form anions, and they like electrons. So we're going to talk about sort of ionic bonds first, but what we typically see is, as we talked about, group 1 and group 2, kind of the left-hand side there of the periodic table, we're going to see cations being formed. upper right where oxygen is, we're going to see a lot of anions and negative charges being formed. So let's take a look at an example of an ionic compound, and that's lithium fluoride. And it's made up obviously of lithium and fluorine. Since lithium is group number 1, it will have 1 valence electron. Fluorine is group number 7, which means it will have 7 valence electrons. And if we look at the electron configuration for lithium, it is 1s2, 2s1. And by the way, that is the 1 valence electron we see in the picture. And if we look at fluorine, which is 9, 1s2, 2s2, 2p5, and 5 and 2 is the 7 valence electrons that we see there as represented in dots, as they are both on the second energy level, right? So those are the 7 valence electron, also group number 7. So in this case, we have a metal and a non-metal coming together. Because of those periodic trends, what's going to happen is lithium's going to go, no problem, go ahead and take my electron pretty much, yeah? And when lithium does that, it is at that point that lithium will then become positively charged as it has lost an electron. When we look at our fluorine will then, we'll do the opposite colors there, I guess. Gained an electron, right? And because of that, it will now have a negative charge. And it is that positive charge and that negative charge which is holding this together. There is no sharing of electrons, and this creates an ionic bond that's happening here. You could also see when we draw this a couple of things. We actually have the charges drawn in because these are ions, so that implies that there's no sharing of electrons. I also put brackets around the anion, the negatively charged guy. You can bracket both if you want, but you should at least have brackets around one of them to indicate that there's no sharing of those electrons as well in an ionic compound. So when you draw these sort of Lewis structures for ionic bonding, this is the way you should represent it. Any questions on that? Now, what happens with our electron configuration? Well, if we come back, we know that our lithium here lost that electron, which means when it becomes Li+, it will have an electron configuration of 1s2. Our fluorine has space in that p subshell, right, for that electron that came over, and it's able to park it right there in that p subshell, and it will gain an electron and end up with an electron configuration of 1s2, 2s2, 2p6. That is 2 electrons. Periodic table number 2 is helium, yeah? That is 2, 4, and 10 electron configuration. 10 electrons is neon. And this is, again, as I talked about before, the overall basis of all bonding, including ionic bonding, is both lithium and fluorine have now achieved noble gas configuration, right? They achieved their isoelectronic with lithium with a +1 charge and helium, so they're same electron configuration as helium, and F minus is the same electron configuration as neon. They become just like noble gases in terms of electron configuration, which is the goal of all bonding. The goal of all bonding is to end up there in group 8 and be just like everybody in group 8, very stable. We also talked about, I think yesterday as well, they do not become those elements, right? Because they still have the correct number of protons for lithium, and they still have the correct number of protons for fluorine. So since we're not touching anything with the protons, they are still those elements, but in terms of their electrons, they become just like the noble gases, which is the basis of all bonding. Any questions on that there? So if we take a look at that, that's what I just drew there. That's good. So as I mentioned before, that is pretty much your ionic bond. It is that electrostatic attraction between the positively charged cation and the negatively charged anion that's holding that together. Once again, there's absolutely no sharing of electrons basically happening in this case. Now, if we look at another example like calcium oxide, calcium is group number 2, which means it has 2 valence electrons. Oxygen is group number 6, which means it should have 6 electrons. And if we look at the electron configuration for calcium, it's a little argon 4s2, and those are the two valence electrons that we see. If we look for oxygen, it is 8, 1s2, 2s2, 2p4, and that is the 6 valence electrons that we see. Once again, we have a metal and a non-metal coming together, which means my metal is going to go ahead and take, going to go this way and give up those electrons. When it does so, it's at that point that my calcium has just dropped 2 electrons, which means it will now end up with a positive 2 charge. Our oxygen in this case will then pick up those 2 electrons. Make it a different color. Pop one there, pop one there. Because it gained 2 electrons, it will have a negative charge. And again, we will form 2 ions that are held together by the opposite attraction there. Now, in terms of the electron configuration, once again, it is going to be these 2 that the calcium loses, which will bring it back to 18 electrons, which is the same electron configuration as argon. The oxygen, again, has room in its p subshell for those 2 electrons that are coming in, and it's going to fill that p subshell up to 1s2, 2s2, 2p6, which is 10. R will hit neon's configuration. So once again, both of these guys, through transferring electrons, basically will achieve noble gas configuration. As we talked about with these representative elements, they will back up to the noble gas that comes before them. The metal, when it loses electrons, the non-metal will go forward on the periodic table to the noble gas that comes after them when it gains electrons. Once again, that is pretty much the basis there of ionic bonding and any bonding. Any questions on that? Now, what happens if we do a little mix here of the 2 that we just did? Let's say we took calcium and we put it together with fluorine that we saw earlier, which has 7 valence electrons, 1s2, 2s2, 2p5. Now, when this goes to lose electrons, my calcium is going to send one over here to my fluorine. At this point, can the fluorine take any more electrons? Well, it could only hold 6 there, right? And again, it just filled up basically, right? So at this point, that fluorine cannot take any more. And if calcium can only lose 1 electron, and if you look at the periodic table, looks like this. If it loses only 1 electron, it's only going to back up to potassium, right? And that's definitely not noble gas, right? It's just alkali metal. So that's not going to be good for calcium. So fluorine will be okay, right? Because it's able to go forward and hit its noble gas. So in this case, because of that, we actually need not 1 fluorine, but we actually will need a second fluorine to take in the next electron for calcium. This is going to allow calcium to lose 2 electrons and once again become positively 2 charged and hit argon's configuration. That will allow my first fluorine to pick up not 2 electrons, but only 1 electron. I'll circle it maybe, and become negatively charged. That will allow my second fluorine to also pick up 1 electron and become negatively charged. And now each of these fluorines picked up 1 electron, which will give me an electron configuration of 1s2, 2s2, 2p6 for each of them. Each of these guys have now hit neon's electron configuration. So all 3 of these guys, the calcium and both of the fluorides, have now achieved noble gas configuration. For the fluorides, gaining 1 electron each. For the calcium, using both fluorides to get rid of both electrons that it needs to get back to noble gas configuration. This is the reason why perhaps you remember when you took the previous class, when they tell you you have a positively charged ion and a negatively charged ion, and when you put them together, the overall charge should equal what? Should equal 0, right? And you actually need not 1 to do that, but you need 2 to do that. And the real reason is get an overall charge when you put them together of 0 is that's the simplest way everybody will hit noble gas configuration. And it's actually the bonding aspect of it as to why you do that, to end up with a overall charge of 0. When you put a positive and negative guy together, it allows everybody to achieve noble gas configuration. Again, as you can see, if you did it with just one fluorine and you left it with calcium, you would end up with a positive charge because calcium would not hit that noble gas configuration. Question on ionic bonding and Lewis dot symbols there. Yeah. All right, we're laid up there for today.